We are going to another idea. It is called, again, because we are in this chapter of electric potential, so everything we are discussing is about electric potential, but this time we are going to discuss about some continuous charge distribution. What is a continuous charge? Let's first try to define that. A continuous charge is nothing but a series of charges, small charges. So, a series of small charges, but they are so close, very close to one another. As a result, they form a continuous charge. That is what a continuous charge distribution is. Now, we are speaking about these charges. These charges, let's say we are assuming at point P, and there are these continuous charges, point P. This point P by itself has a position vector as r vector. Position vector is nothing but it is coming from the origin. Now, we know that electric potential at this point P is given by 1 by 4 pi epsilon naught summation. Instead of summation, I'm going for integration, right? Q, I'm going, because I'm speaking about integral, I'm looking at as a change, small change. So dq, then r vector minus ri vector. So that is the electric potential, which is same as the previous formula we just derived. So we are speaking about multiple small charges. That is why instead of simply going for Q, I have gone for dq. So now dq is made up of, look at it something like this, multiple or several charges, and when you add them, you add up to a volume. Right? Now they are made up of some volume. So from this, so these charges, they are distributed over a volume. Okay, so let's say the volume is dV. Whatever the distribution, the surface, the volume we are looking at, there is a mass, just some volume, so that is dV, the volume of that. Multiply volume by rho. Rho is not our usual density, that is charge volume density. Now let's see this, understand it further. Okay, now what is rho? Rho is nothing but charge volume density is simple. It is nothing but charge per volume, per unit volume. That is charge volume density. So rho equals charge per volume. Now if I multiply rho by volume, I get charge, which is dq. That is the reason I have substituted dq with this dv into rho. Now this gives me the charge that is distributed over a volume. What is charge distributed over volume. Look, compare with some spherical object which is made up of small pieces. Now we could imagine our favorite sweet laddu. So if you look at your laddu, it looks like this, spherical, but it is made of some small pieces, right? And imagine these pieces to be charges, and they all build up together to form a volume, right? Now each of this charge, now how much charge is there totally, right? So that is the total charge, and then volume of the sphere, that gives us the charge volume density. What we are doing is we are calculating the potential due to the charges distributed over a volume. So if you do that, like imagine, you have to imagine a laddu made of small pieces for this. So you go by the previous formula, 1 by 4 pi epsilon naught. We do this integral calculus over the volume, the entire volume of laddu. So given by q, we saw it dq, we are now replacing it rho into dv divided by r vector minus ri vector. This is the charge distributed over the entire volume. Now instead of volume, what if I look at the charge which is distributed over surface area? So we are not considering the individual particles of laddu. We are just looking at the charges which are present on the surface area of laddu. So in that way, Vs should equal 4 pi epsilon naught, and then we are integrating over the surface area of laddu. Now here, instead of having dq, what I'm saying is I'll look at how much charge is present per unit area. So charge by area, that will give me surface charge density. So earlier we saw volume charge density because we used volume. Now I'm going for surface charge density because I'm looking at only the surface area. That is given by sigma. That way, sigma into area, I'm taking area as ds. So sigma into ds, that will be dq. We divide it by usual r vector minus ri vector. This means our Vs equals integral calculus S over the surface area sigma into ds, integral calculus sigma into ds by r, integral calculus sigma into ds by r vector minus ri vector. Let's remember the key thing which we have learned here, the surface charge density. We are using sigma for that. So we used the charge, and we computed the charge due to volume, we computed the charge due to the surface. Now we could also look at the charge due to line, right? So that is called VL, the charge due to line density, okay, which is equals 1 by 4 pi epsilon naught. We are integrating this over the length of a line. So for surface, for volume we looked at volume charge density. For surface we looked at surface charge density. Then for line we would look at line charge density. For line, we look at line charge density. Now that is given by lambda. Now that is given by lambda. Lambda equals the charge divided by length, which I'm keeping it as dl. Okay, so dq equals dl into lambda. This we are going to call as line charge density. This is line charge density. Now let's look at the other density: surface charge density, then volume charge or charge volume density. We have three kinds. Now let's go back to our formula. So if we substitute that, it becomes lambda dl by r vector minus ry vector. So we have, so this is the, what did we find here? This is the charge distribution over a line. Now the continuous charge distribution, is going to be the summation of the charge distribution due to the volume, the charge distribution over the surface, plus charge distribution over the length of the line. Or if you go for this, it is going to be 1 by 4 pi epsilon naught. It is the common term across. So we do the integral over volume, then volume density, we multiply it by volume, r vector minus ri vector, plus we do it over surface density, charge surface density multiplied by the surface area, r vector minus ri vector, plus integral over length, line charge density multiplied by length of line, r vector minus ri vector. This is an important result which speaks about the potential, electric potential due to a continuous charge distribution.